So last class, this is kind of where we finished. We said a mole is equal to the mass on the periodic table. A mole is equal to Avogadro's number. We also said we're pretty much never using this relationship. It was about the mass of like protons and neutrons, and we're at the most concerned with atoms. Yes, you all can ask questions. This is not just a video for you because you're present in the room. Oh, Flappy Bird. It's also a video for future young learners all across my viewership, all 142 of them. Across, yes. All right, yeah. Don't question the grammar. It's not good. We also had a mole map up here, how to convert from mass to moles, moles to particles, and back and forth. That can be kind of useful if you're challenged with dimensional analysis. This is a tool to kind of get rid of the decision making up. Should I put it on the top or the bottom? Kind of go, well, if I start with grams and I'm going right, it's on the bottom. If I start with moles and I'm going left, then the periodic table's on the top. And it kind of like removes that decision. And you can see it says use molar mass. The only problem with this little mole map is I'm not going to hand you one during the test. Right? So you're going to have to either know how to use the mole map and create it for the test, or you're going to have to know how to use dimensional analysis, and that's on you, not me. All right. So the second topic we're talking about today, percent composition, and then we're going to talk about how to calculate formulas from data, how to figure out, AL203, looking at mass data. And this actually how old chemists way back did it before we even knew the periodic table was a thing. As they were creating the periodic table, this is kind of how they created the periodic table, sort of look back in time. First we start with mass percent of a given element, and mass percent is very easy. You go to the periodic table 17,000 times, you find all of the elements in question, and you calculate the percentage. Just like you calculate anything else, like what percentage of the class is wearing white shoes? I calculate, oh, look, there's 7 people wearing white shoes, and there's 21 people in the classroom. Well, that's 7 over 21, percentage-wise. And so you go, 7 people divided by 21 times 100, and that's 33%. Oh, good, my pen still sucks. Oops, I just recorded that. That makes it fun for the other people, too. All right. And if you're staring at your phone to figure this math out, I just did 7 divided by 21. That's 1/3. 1/3 is 33%. Does the 21 include those 7 white-shoed people? Yes. Even that guy that only has 1 white shoe on in the boot. And I even included him in my calculations of this. I guess I should have been 7.5-ish. I don't know. Maybe 6.5. Subtract the 1 boot. So in terms of our life, though, in terms of chemistry, we go to the periodic table. So I'm gonna do this question. What's the percentage of carbon in carbon and 4 chlorines? So this is carbon. Where did I get 12 grams for carbon? They said periodic table. They are correct. And on the bottom, it's carbon and 4 chlorines. This is also from the... Ooh, they said it with enthusiasm that time. You probably almost heard them at home. Periodic table. And then there's 4 chlorines. See, there's 4? There's 4. So multiplying that by 4 and then adding it together. So I can't do that in my head. So I have to pick up ye old calculator. It's actually an abacus from the 18th century. For those of you at home, it's a calculator. Visual aids don't come through in the videos, except for what you see, filling the time with my... Okay, so 12.01 divided by that number times 100. Ooh, neat, special. So this is 7.81% carbon. Is there another element other than carbon? How many other elements other than carbon are there? In this question. Just chlorine, right? There's carbon and chlorine. So if I asked a follow-up question like, hey, Francois, what's the percentage of chlorine? Which it literally says as a follow-up question right there. There's 2 ways to do that. There's the easy way and the hard way. Which way do you want to do? The easy way. percentages have to add up to what magical number? 100. So if the carbon is 7%, then the chlorine is the other rest, right? About 93%. It would be 92.19% chlorine. But if you don't believe me when I do that subtraction, you could also do it the same way we did this carbon. You could say 4 times the chlorines on top divided by the total again on the bottom times 100, and you're going to get that same answer. You might have a slight difference in the sig figs and the rounding afterwards. Was that your question, Lewis? Yes, okay. Lewis was actually going to ask about sig figs. He put his hand up. Yeah, I'm looking at this, and I was like, okay, I've got 4 sig figs and 35.45. I've got exactly 4. That's the exact value 4, isn't it? So that's infinite sig figs. All right? And then the bottom had 5 sig figs. So between infinity, 4, and 5, I went with 4 values. So I wrote down the first 4. Okay? If you did the subtraction method versus the math method, the only time I see a difference is in the estimate. And it's okay if the estimates are different because they're estimates. Cool? So, you people at home, that means you kids in class, it's you tomorrow, all right? Aloysius. All right. I want a third of the class to do sodium, and this question, a third of the class to do oxygen, and 1/3 of the class to do hydrogen. Go ahead, this is the compound NaO, sodium hydroxide. Look them up on the periodic table and calculate the percentage sodium, the percentage oxygen, or the percentage hydrogen. And I will be back in 30 seconds. Pause the video and calculate. That was a really good observation, Aloysius. That was a really good observation. I really liked that. I like the question you asked there. Let me just go over what Aloysius said. It was about sig figs, and it was 4 sig figs over 4 sig figs times 100%. So there's 4 sig figs in this answer. Good job. And then in this one, it was 4 sig figs, 4 sig figs, and the 100's perfect. Like that's the definition of percentage per 100. So that's why I'm not factoring that into my thought. There's 4 sig figs in that one. And then the last one, and this is where Aloysius was like, well, that's got 3 sig figs. Is that why you only have 3 sig figs in the hydrogen? I was like, yeah, that's right. That's exactly right. Nice job. I don't know if you've noticed it. I just noticed it as I was rambling about my conversation with Aloysius, that this does not add up to 100. If you take the 3 percentages, it accidentally adds up to 100.01. But that last value is the estimated value. So is it okay that the estimated value is the one that's funky? Yeah. It's quite often the funky one. If I had asked Francois back there to do this instead of looking at his phone, he could have done this one, and subtracted from 100 to get that last one, and he would have adjusted the percentage to 2.52, and that would also be fine. It would only be in the estimate. I said the 3 times, if you didn't catch that. It's very important, does. How would we do this one down here? Oxygen in hydrogen peroxide. What would go on top? Hydrogen would go on top? It's oxygen. Yeah, oxygen would go on top. So what is anyone know the mass of oxygen? I got like 6 different people said 16. Cool. Now, do I just write 16? Or what do I have to multiply it? And what do I multiply it by? By 2. There's 2 oxygens. I have to multiply it by 2. And then it's divided by all of the pieces. The 2 hydrogens and the 2 oxygens. And we multiply that by 100. So that's 34 over 30. Hey, that's already wrong. That's what happens when you try to use your brain instead of a calculator. 32 over 34.02 times 100. We'll pause there for calculations. So that's 94. That's a 9. It kind of looks like a backwards R. Sorry, my pen's being a little funky. Let's try the eraser so it's a little clearer. There we go. So 94.06% of hydrogen peroxide is oxygen. And off camera, I will ramble about oxygen, but not right now. So, do you guys need a second to copy this down? I could pause the video if you need a second to copy it down. All right. That joke fell over like a ton of lead, which is the same as a ton of anything else, because a ton is a ton. It doesn't matter what it is. Although a ton of feathers would be way less painful than a ton of lead. What's that? No, they didn't hear my joke. But they're still laughing, because that's what's required of them as my minions. Hey, wait a minute. I'm recording all of this right now. We need to pause. So these two terms, empirical formula and molecular formula. Let's start with molecular formula. So a molecular formula represents the actual molecule. Your body's made of all sorts of molecules. One ridiculous one, deoxyribonucleic acid. What's the common name for Aloysius? DNA. Good job, Philip. Good job. Yep, also DNA. DNA is way too big for us to deal with. Cool? But it is actually just a giant spiraling molecule of covalent bonds, but it's too nasty to deal with. Let's deal with something a little bit tastier. This molecule is the formula for glucose, aka simple sugars. It's pretty tasty, kind of sweet. And this is the actual molecule's formula, 6-12-6. Is that a reducible formula, though? Is the ratio reducible? What are all of those numbers divisible by? 6 or 2, right? Or 3? We're going to divide them all by the largest thing. Divide them all by 6. Divide by 6. And we're going to reduce it to what's called the empirical formula. So the empirical formula would be C1H2O1. And that ratio is not the right formula. That's a completely different substance. But it's the same mass ratio. If you grab from the periodic table and you go 12 times 6 plus 1 times 12 hydrogens plus 16 for oxygen times 6, you get 180 for the mass of this big molecule. The mass of this molecule would be 30. Because what's 180 divided by 6? 30. But it's the same elements, and it's actually the same mass ratio. It would be 12 times 1, 1 times 2, 16 times 1, adding up to 30, but the percentages would be the same. And so they have the same percentages if you grabbed them off the periodic table and worked it out. But the molecular formula is the actual combination, and you could draw the shapes and how they attach. But changing the ratio from the molecule to the empirical has a huge impact. I said this is a nice sweet molecule called glucose or sugar. This other one up here is formaldehyde, which is used to preserve dead bodies and not delicious or anything like that. You don't want that on you or in you or anything. And so since they have the same percentages, we use this difference in mass to figure out what the actual formula is. Since this mass is 6 times heavier than that one, we can kind of figure out the real ratio of our molecular formula. Let me throw one more up there. This is a pretty funny one. That's the molecular formula for laughing gas, N2O4. What's the empirical ratio for N2O4? Yep, NO2. You don't have to write the 1 down. I'm just trying to preserve the 2 to 4 ratio is the same as a 1 to 2 ratio on the board. We don't usually write the 1s because we don't want to use up all our pencil lead so quickly. So we save the 1 lead for later. Again, laughing gas is not anything similar to this other molecule. I can't quite remember what that. I usually say this other one is what they inject into car engines to make them go faster, but that might be a lie. I might just make it stuff up. But this one is actually laughing gas. The same ratio, look, but just twice as much as the empirical. Calculating an empirical formula can be a little nasty. So I have the steps in your notes. This is not very readable, is it? It's not. So I'm going to reduce these. I'm going to go back a page, insert page before, and I'm going to write down the rules in 2 steps, maybe 3 steps. Step 1, convert grams to moles. Where do we find the mass and mole relationship? You can't hear the cricket on the video right now, but that's the only thing making noise when I said that question, is the cricket in the corner of the room. And there is really a cricket for those of you at home. I don't think I can get the cricket on the microphone. I'd have to find the cricket, and then it wouldn't survive. Yes, you in the back, Josephine. Oh gosh, okay. Yes, grams to moles. I use that 1 mole is equal to the molar mass to make that one happen. Yep. So I'm going to go to the periodic table, PT for periodic table. Anytime we convert grams and moles, we're using that relationship, 1 mole and the molar mass. And then, once we have moles, we need to look at the ratio and adjust the ratio. Let me just kind of show an example. If I had x was 1 and y was 1.5, that is the same ratio as 2 and 3. If I multiply both of these by 2, I have a nice whole number ratio, don't I? All right, so maybe I have to multiply them both by 2, adjust the ratio. More commonly, though, the more common thing is to divide by smaller moles. So it's really common to have decimals in your answer to step 1, and you have really nasty ratios like x is 0.04 and y is 0.16. And those, it's not a very pretty ratio. Which number is smaller, 0.04 or 0.16? 0.04. So we divide by the smaller moles. We divide them both by 0.04. What is 0.04 divided by 0.04? 1. And then the other one, 16 divided by 4 is 4. And so we get a nice clean ratio when we divide by 1. All right, divide by the smaller one. Cool? Billy, did you have a question? No, just stretching. Okay, just want to make sure I got it. All right. Josephine, you good back there? Chilling. All right, I was chilling. So here's the 2 steps. Convert grams to moles. Adjust the ratio. Adjust the ratio usually means divide by the smaller. Occasionally it means multiply by 2. All right? And just let your calculator handle that. So let's look at this example that's completely worked out in your notes. Is this completely worked out in your notes? Cool. So I had these 2 masses. I'm going to do first step. Convert mass to moles. I went to the periodic table and got the mass of aluminum, and I got this many moles. I went to the periodic table for oxygen, and I got that many moles. And right now, my ratio looks disgusting. 0.154 is the subscript for aluminum, and then oxygen subscript is 0.231. That is not a nice ratio, is it? So I divided by the smaller number, and I got 1 and 1.5. Is 1 and 1.5 a better ratio? It's better than the previous one, but it's still not whole numbers. We need to get all the way to whole numbers. So I adjusted the ratio one more time by multiplying by 2, and I got a nice ratio. I'd also like to point out that that ratio comes from the charges on the periodic table. Last chapter, we did nomenclature. And you would grab aluminum is a +3. Oxygen is a -2. What did we do with the charges? Swapped them down, and we had a 2 to 3 ratio. This is actually how we figured out the charge ratio. We chemists, not we high school chemists. The chemists took the masses and did the math to get the ratio, and then found patterns that they then interpreted those patterns to get the charges. Now you guys start with the charges and use the patterns that have been observed by someone else. And the next example is not worked out, but we're going to do the same steps. We're going to take the masses and convert to moles, and then we're going to adjust the ratio. So we start off by writing down all 4 of these compounds. 1.3. Damn. I'm just singing a song. I don't know why you're giggling out there. It's not like I almost recorded a curse word for public consumption. No one's ever heard curse words, so it's a good thing I didn't. That much lead. Is this the amount of hydrogen? I feel like there's a typo. Is that what it says? All right. Grams of hydrogen. Oh, yeah. I'm actually going to pause the video for a second, and let you all at home or in class or, I don't know, on the bus, wherever you are watching this video. Or for those of you trying to go to sleep, now's a good time to start because you're probably getting bored. Not in class. I forgot what I call you. What was I calling him? Francois. He's Francois. He's Josephine. She's Aloysius. All right. There's a lot of odd things going on for those of you who can't see. So, change mass to moles. Woo, woo. Mass, moles. Woo, woo. Mass, moles. Woo, woo. Mass, moles. Woo, woo. Mass, moles. You got to do that 4 times. How about I pause so you don't have to watch me write? And go to the periodic table, find these masses. So, I'm recording you in BT dubs. So I took the mass, I went to the periodic table, and I found every element with a little help from my friend Billy there. I have all the elements, and now I'm going to convert them to moles. And I'm going to pause because you don't want to see me type that either. Alrighty, so did the math. Whole lot of 6s up there. And so we've done the first step. We converted the mass to moles. This is tedious. This is where teenage Russell, made simple errors. Teenage Russell might have left out a 0 over here or something like that. So be very careful when you write down your stuff. Those of you with Aloysius handwriting, you know that you need to be careful because you'll make errors. Adjust the ratio. My suggestion was divide by the smallest. Which of those values is the smallest? The one with this one. That's the smallest one. It's 0, 0 versus only 1, 0 versus only 1, 0, 0, 0. That's a 6. That's just higher than a 5. So we divide them all by this number. And this is the one math I can do in my head. What is the answer to that one? 1. Now when I do this one, also dividing by that smaller value, I am going to get something very close to 1. I believe it is going to be I'm typing, so just give me a second. I typed the wrong number. Yeah. So I got 1.001. Are we okay with just calling that 1? Because I am, because the estimate is the last one, so this is practically 1. And I divide the other 2. And I feel like I'm supposed to know this in my head, but I don't, so I'm going to actually type it down. Again, being very cautious to type the numbers perfectly. Ah! Whoa! Huh? Huh. Okay. 10. Wow, that feels really wrong to me. I'm going to check my math there. Oh, it has 1 0 instead of 2, so it's going to be drastically different. Thank you, Josephine. There's not actually a Josephine in my class. That's a code name for that person in the back. What? Why did I divide by 16? What am I doing? You are speaking to the future right now, which is different than speaking to the past. You just look weird when you're doing that. I'm going to actually go back and test that one number. I feel like I made a mistake typing somewhere. I did make a mistake. Right here. There's a 0 right there. Ah! You might get older, but you don't get any better sometimes. I left out a 0, which means this is not 10, but it's actually 1. You know how I said that felt weird? We don't usually have like 1, 1, 10, 4. And I was like, God, that's really weird. So my formula is PB 1, because that value was a 1. And then H. What's the value for H? What's the value for arsenic? 1, now that it's been corrected. And then oxygen is a 4. And can that be reduced? So that's the ratio. That's the right ratio. Okay? That's the empirical ratio. PB1H1SO that is lead monohydrogen arsenate. Not that you needed to know the name of that, but that's what it's called. Convert the mass to moles, divide by the smallest. Yay! If we'd had a fraction in there, like say one of them came out to 1.5, we'd have to double everything. All right? So we just take the 4 answers and multiply them. All right. For those of you in class, you probably can pause this. Those of you here, too bad. I am only going to reveal the answer in one little bit about this one. Come on. Scroll down. Those are the 2 things I'm going to give you. Those of you in class have to work your way to that answer. So the difference in this one is the vanadium reacts with oxygen to make that new mass. That new mass is both vanadium and oxygen. You have to subtract to find the mass of the oxygen and then go through the same steps. All right? Yes. And I forgot your name. And Francois. Yes, Francois, you may use le restaurant. Le pâté. Not party, potty. There's also one completely worked out on the next page from beginning to end. The only difference with this one, is that I can't click the right pen, is that they gave percentages. And take a look at what they did with the percentages. They took 65% and just wrote 65 grams. So they didn't actually do anything. They just pretended it said grams and worked the problem the same. Lastly is comparing molecular formulas and empirical formulas to figure out the mass difference. We already kind of did this. We said the one molecule was 180. The other molecule was 30. How much times heavier is 180 from 30? 6. So the formula must be 6 times bigger. Okay? The formula must be 6 times bigger by comparing the 2 masses. So let's look. Oh, go back. Sorry. I heard a no. He keeps taking pictures of me. It's a little creepy. So here we have this formula here, which I go to the periodic table, and I have 30.98 times 2 plus 16 times 5, and that's 142 grams. 284 divided by 142, the molecule is twice as heavy. What is P2O5 times 2? P4O10, that's an 18, you moron, 10, and that's the formula for the molecule. And you can check and make sure it equals that mass that they gave. The molecule is twice as heavy as the empirical formula, so the formula should be twice as much. I think, yep, that's the end of the notes. And what I want you to do now is worksheet 2. Really delve deep into worksheet 2. It has a bunch of these problems on it, as well as some of the old ones. Good luck, live long and prosper.